Dear student, let us begin the lectures on machine design part 1. This is the lecture number 40 and the topic is design of brakes. This is the concluding part of the lecture on the same topic. Now, in the last lecture, that is in lecture 39, we have discussed how to get the pressure distributions or how to get different forces in a type of brake which is known as shoe brake. And there are few other brakes which we are going to discuss today. But before that, let us go to the shoe type brake again and discuss something very quickly the internal or external shoeing arrangement. So, basic kind of shoe type brake can be taken as, say, this is say the drum, and we have the shoe here, brake shoes, there are two symmetrically placed levers, so this is the center of the drum and at symmetric angle there are two levers and on them there are these shoes. So, there are friction material symmetrically placed again. This is internally, this is internal radial shoes and the force is applied here by some mechanisms, and then it it rotates, these two calipers rotates about these two hinges, and then the friction material gets pressed and it develops the frictional torque. Now, if we take these two angles to be theta 1, we measure this angle from this point, let us say this is theta 1 and this one is theta 2. Then the pressure distributions, of course, I have not discussed how to get the pressure distributions, but the pressure distribution looks something like this. This is the pressure distributions. So, at any angle theta, now measured from this point, this line, theta is measured from here. So, at any angle theta, it is P max divided by sin theta max, and maximum value of theta is theta 2. So, this is the distribution of P. Now, once this distribution is known, we can find out what will be the force required to apply this brake, and what is that force required. Now, it of course, it depends on P max. Now, for different friction material, the P max is limited. So, once we know this P max, we can find out the maximum P theta. P theta is known because P max is now known, this distribution is entirely known. From this we can apply, we can find out what will be the value of F. Now, in order to find the value of F, we will have to use some force balance or moment balance equations. Now, if you consider a small element over here, a very small element where the force acting is P theta times r d theta. If you consider the unit distance, unit width of the drum, then along the cylindrical coordinate, that is along this axis of the brake, along the axis of this drum, then this is the entire force, and we have to calculate two moments. One moment is the moment we are calculating moment about this point O. Now, there are two forces, one is this P theta r d theta and another is friction force. So, if you take friction force, that is, it is rotating such a way that the friction force is acting along these directions, then this is P theta mu times P theta times r d theta. So, therefore, we have to calculate now two moments, that is moment of this force, this is nothing but P theta times r d theta normal force times this distance, and this distance is nothing but this distance, which is the perpendicular distance, and if you consider this length to be, let us say, a, then this is nothing but a sin theta, as you can verify, because this angle is theta. So, therefore, this is a sin theta, and this is the moment of this this force P theta d r theta, and we will have to integrate from theta 1 to theta 2. This gives the moment m 1. Then there is another moment m 2 due to this friction force, and what will be that? That will be if we can write down, if we can erase this one, then this is m 1, the m 2 could be written again this integral theta 1 to theta 2, and now this force mu times p theta r d theta times this distance, and this distance will be r minus a cosine theta. So, once we know this m 1 and m 2, then taking the moment about O, we can find out what will be f. If we know this distance from O to f, that is, we can get f times O f plus this is the distance and this is the force, and let me not write down this vector notation here, it may be confusing. So, this is f times O f plus m 1 plus m 2, of course, taking the proper sign, this is equal to 0, from which we can find out what will be what the correct value of f required. Then another thing which is very important for design, that is there are pins over here. You see there are pins where it is hinged. Now, the pin reactions will be present, and how to estimate this pin reactions? Those are coming from the force balance equations. Now, once you draw the free body diagram of this caliper, then there are forces F here, then distributed pressure P theta and friction force mu times P theta, and those are balanced by this reaction forces R x and R y. Now, moment balance is already done, the force balance has to be done in order to get R x and R y. So, once this R x and R y are calculated, then we can find out the dimensions, proper dimensions of this pins. So, that actually ends the design of this shoe brake. Now, this was already taught in the last lecture. Now, we have to go ahead. Let us go to the next kind of brake, which is known as band brake. Now, band brake, this is the brake which looks, now this is the drum again, on the top of which there are so this is the drum and this is the band which is connected to a lever. Let me show by, so this is the lever. Now, this is the band which is wrapped around this drum. Whenever, and suppose this is rotating along this directions, we want to put brake. So, therefore, then we put a force, let us keep a force such that this braking torque is applied. How to give this force? What is the direction of this force? We see that whenever this lever arm is given a force, then T 1 and T 2, let me say this is T 1, this is T 2, these two forces are developed, that is the tensions in the band, and whenever this we want to apply a brake, then T 1 must be greater than T2, that is T1 minus T2 times r will be the, if r is the radius, T1 minus T2 times r will be the braking torque, and that must be positive. So, therefore, T1 is positive, and that can be done only if we apply force in these directions. So, this is how the band brake operates. Now, we know that whenever this drum rotates, so there is a definite relationship between T1 and T2. If the kinematic coefficient of friction is mu, then if we consider a small element measured from this point where this band touches. So, at angle theta we consider a very small element. Then if you consider that particular element, then there will be tension here T, then this, because of the friction force, the T varies. So, this is T plus delta T, and this angle is nothing but delta theta. So, whenever you and of course, there will be the friction force acting over here. So, this is friction force mu times n and the normal reaction n. So, if you calculate the force balance, then what you get this following relationship, that is dt by t is mu times d theta. So, when we integrate, then ultimately after integrations from theta 1 to theta 2, if this is the theta 1, that is theta is measured from this point. So, theta is, of course, theta 1 is 0, and this goes up to this point, that is entire angle, this is theta 2. So, theta 1 to theta 2, what we get is the following relationship, which is very well known. This is T1 by T2 is e to the power mu times b beta. Beta is the total angle of wrap. So, this is the entire beta, this is beta. Beta is the angle of wrap, that is the angle through which this band is wound around the brake, around the drum. So, this is the total angle. Now, you see T, this is greater than 1. So, therefore, T1 is greater than T2, and we can have a braking torque. Now, if we consider the free body diagram of the lever, so this part is known where mu is the coefficient of frictions. Now, once we get the free body diagram of the lever, then it looks like so this free body diagram of the lever, this is, of course, this is hinge point. So, we have a force T2 here, and we have T1, and it is counterbalanced by P. If these distances are A and this distance is L, then of course, taking the moment about this point O, we can find out this P, and P comes out to be, it is very easy to check that P becomes now P will be equal to T1 A by L. So, this much of force has to be applied. Then again this for the design considerations, we will have to check two things. One is this T1 is of course the higher of T2 and T1, and T1 should not be too high. Then what happens? Then the band may get snapped, and that is what we do not want. So, therefore, the maximum value of T1 has to be limited. So, the design consideration says that T1 must be less than sigma allowable times A of the belt. So, this consideration has to be taken. Similarly, because there is a continuous change in the tensions. So, there will be the continuous change in the normal pressure, and this normal pressure is of course limited for a friction material, otherwise there will be wear and tear. So, we have a max limiting value of the normal pressure which the friction material can withstand, and so that has to be again considered. So, this is a type of band, this is known as a band brake. We have another kind of band brake which is known as differential band brake. Let me draw that. So, this is the drum and we have this lever, so this is the lever. In the last case we had fulcrum at the end, but now here is the fulcrum. Then the band, so this is the band which is making an angle 90 degree. So, this is one part of the band and the other is here, and suppose this is rotating in the clockwise directions. Then of course, in order to apply the brake we have to have T1 greater than T2. So, T1 is greater than T2 if T1 is the tension appeared in the taut side and T2 is the tension appeared in the slack side. Then we have to apply, this is the fulcrum hinge. This is the hinge. We have to apply a force, again we have to apply a force over here. Now, here the analysis again remains same, T1 by T2 remains e to the power mu beta, where beta is the total angle of wrap. Now, you can see that the total angle of wrap is this angle, this is beta. So, this is known. Now, we consider the free body diagram of the lever. Then if you consider the free body diagram of the lever, it looks somewhat like this. This is the hinge, this is T2, this is T1 and this is P and this is the hinge O. Now, this distance, perpendicular distance, let us take B and this distance A, whereas the end to end distance is L. Then what we have is if you take the moment about O, now writing the moment about O equal to 0, we get the following thing, that is P times L minus T1 times A plus T2 times B equal to 0. So, therefore, the total force P required is nothing but, if you can write down this, then you get P L is T1 A minus T2 B. Now, if we can see that T2 B is actually helping the lever to apply the brake. So, it may so happen that T2 B is greater than T1 A. So, this term, if it becomes negative, if it becomes positive, then of course, our chosen direction is right, and if it becomes negative, you consider the case when this is negative. Normally this is positive, but if you consider this case when this is negative, then what happens? Then P is negative, that is we have to apply the force in the opposite directions. And what does it mean? We will have to apply a force to disengage the brake, that is the brake is now self locking, it gets itself locked and we have to apply a force in the opposite direction such that it gets unlocked. So, this is a self locking situations. We had another occasions to study about the self locking in the connections with the shoe brake, but this occurs also in a differential band brake. So, this is known as a differential band brake, and if this term is less than 0, then the condition is called the self locking conditions. So, this is self locking, and here the condition is that A by B less than equal to T 2 by T 1, and we know that this is nothing but e to the power minus beta mu b. So, therefore, if this condition is satisfied, then it gets self locked. Now, the complete analysis will be different if this one, that is, instead of clockwise rotations we had anti-clockwise rotations, then of course, we will have to make the analysis in a different way, but the procedure remains same. We can have self locking situations in that case also, but the actual conditions will be little different and we will have to find it out. Now, this is known as a differential band break. There is another kind of break which combines the two things, band and the shoe type break. So, we have studied two things, one is band break, then differential band break, and we can have shoe and band break. So, this is band shoe break. So, this is a combination of two kinds of break. Let me discuss it with one figure. So, we are now going to study this shoe band break. So, this is the drum, now there may be, so there is a band over here. Let me consider this is the lever, then there is a band, and between the band and this drum we have different shoes. So, there are, let us say, n number of shoes. So, there are n shoes. Again this is the fulcrum, it is rotating in the clockwise directions. So, definitely T 1 is greater than T 2, and we have to apply pressure of force over here P. Now, what is the relationship between T 1 to T 2? It is not like T 1 by T 2 is e to the power mu beta, because it is not continuously distributed. So, this equation is now wrong, but we will have to find out what is that equations. Then it is very easy to find out if you consider particularly one block. Let us say we consider this block, the free body diagram of that block, and then find out what is the change in the tensions when we move over from one block to the other block. So, let me now write down the free body diagram of one such block. So, this is a block where T 1 this is that block, we have T 1 here, and this is T 1 prime, let us say, which is different from T 1. Now, this angle is, let us say, twice theta. Now, this is normally less than of course 60 degree. So, therefore, we have a concentrated, we can take this load to be concentrated. The normal reaction will be now here normal reaction, and of course, T1 is greater than T1 prime, because this drum is rotating in the clockwise directions. Therefore, friction force will be in the anti-clockwise directions, and if you draw it on this particular element, then friction force will be mu times n along these directions. So, if you write down the force balance equations, then you get the following things. Let me write down. So, T1 plus T1 prime again sin theta is equal to n. You see that this angle is almost theta, this is theta. So, therefore, the component T1 sin theta and T1 prime sin theta will be equal to n, and T1 minus T1 prime cosine theta will be equal to mu n. So, if you then make the necessary calculations, you get the following results, that T1, that is T1 by T1 prime is 1 plus mu tan theta divided by 1 minus mu tan theta, which is of course more than 1. Therefore, T1 is greater than T1 prime. Now, this happens for only one block. Now, if you move from this block to that block, then it is, this is T1 prime, it may be T1 double prime, T1 triple prime, and so similarly the analysis becomes similar for this block. So, therefore, we can have T1 prime divided by T1 double prime is the same, and we can proceed so on until we reach T2. So, the relation between T1 and T2 then becomes the relationship between T1 and T2 is T1 by T2 is equal to 1 plus mu tan theta divided by 1 minus mu tangent theta and raised to the power n. So, if there are n breaks in such shoes, then we can get the following relationship. So, this is the relationship between T1 and T2. Once we know this relationship between T1 and T2, then we can consider the free body diagram of the lever as before and find out what is the value of P. So, this value of P is required in order to design this lever, because then we can see that this lever will be subjected to different kind of stresses. If you consider this to be a beam, then this is subjected to shear stress as well as bending stress. So, therefore, the lever has to be properly designed. And again, of course, we will have to consider that the band should not fail. So, therefore, this T1 we have to decide theta in such a way that T1 should not exceed some limiting value. So, this is very important from the design considerations. So, this is what is known as the band shoe brake, because it combines the shoe and the band together. So, this is roughly the different kinds of band brakes. Now, we come to a different kinds of brake, which is known as the disc brake. The disc brake, as the name suggests, that here the brake is a disc type, that is unlike the drum. Here we have the disc which is rotating with some speed, and we will have to apply friction force, that is normal force on the top of it. We apply normal pressure, and since this is rotating, so therefore, a friction force will be developed. So, looked from the top, this will look like this is the disc, and the normal force is applied. Now, the pad dimensions may be different kinds of different kinds of pads are used. If this is a full circular pad, then we have this is the pad, let us say. Now, so if it has the radius r, then there can be two situations. When the brake is relatively new, then we have the condition of uniform pressure. When the brake is relatively new, then we have uniform pressure. In that case, the the distribution that is the torque, braking torque is known. In that case, the braking torque will be equal to braking torque is equal to mu times F times F is the total force applied. If we apply a total force over here, so this is distributed, it is equivalent to a concentrated force F. So, this is mu times F times 2/3 of R2 cube minus R1 cube divided by R2 square minus R1 square. Now, here of course, in this case R2 is the outer radius, this is equal to R, and R1 is equal to 0. So, this is for the uniform pressure, that is the distribution here is uniform. Now, we have a second situations when the brake is worn out, then we have the condition of uniform wear, that is in this case the condition 2 we have uniform wear, that is for the old brake, and in this case T will be equal to mu times F, the total force, times this radius equivalent, that is half R1 plus R2. Here this uniform wear, it means that P, the force distribution, if it is a function of R only, times R is constant. This is the uniform wear conditions, whereas for the uniform pressure P R is constant. So, from this as assumptions, this braking torque is taken to be this one. So, this is the disc brake arrangement when the force is applied axially and the brake this pad dimension is a full circle. There are other situations also, and normally in a modern vehicle we have a sector type pad, where the pad is not a full circle, but the pad may be a sector. Where this is theta, which is theta is roughly 60 degree. This is the sector. So, this is the sector type, this is a sector type brake pad. Here the analysis is almost the same, that is we have to consider up from this point to that point. It is not axially symmetric problem right now, but we can get the analysis quite easily. This kind of sector type brakes are used in automobiles, and the arrangement through which this kind of normal pressure is applied is known as the caliper. So, this is caliper, and this may be fixed to the automobile body. So, there may be fixed caliper or there may be floating caliper. Fixed or floating caliper. So, floating caliper has the advantage that it can adjust itself automatically with the vibrations, because normally the automobile parts will vibrate. So, therefore, the orientation of the disc may be changed, or what is most important, that during the fixations there may be some inevitable misalignment of the disc. So, in order to accommodate this misalignment and other defects, we can have a floating caliper, which is very easily adjustable to this existing situations. So, normally in a very good car, nowadays we have this floating caliper type brake, but they are all disc brakes. Drum type brakes are normally used for heavy vehicles, because they have a very large capacity of giving a braking torque. So, this is roughly the analysis of a disc brake. Again, what is most important for the design is that the pressure on the disc and on the friction pad, because the friction lining can withstand up to a maximum pressures. Also the wear and tear, and again the heat generations. Now, heat generation is something which is very important for design of a brake, because the heat, if it is not dissipated properly, then it will lead to the temperature rise of the brake, and with the temperature rise the thermal instability may set in. That is, the material may not be so effective in the high temperature. The friction coefficient may be small, or may get decreased if the temperature is increased, and all sorts of wear and tear will take place at high temperature. So, therefore, the usual design procedure will be such that is we have to take enough care such that the total arrangement gets cooled down as fast as possible. So, now we have considered few types of brakes. We consider now a general brake and consider the thermodynamic aspects of the brakes. We see that the brakes have different parts. It has disc or drum, then caliper or maybe friction material, friction lining, maybe caliper or lever or band, etc., for applying the necessary friction, necessary normal force. So, there are various components, and the exact thermodynamic analysis is very difficult. So, what we do, that we make the thermodynamic analysis of that part which is mostly responsible for the temperature rise. For a disc type and sector type brake braking pad, it is found that the friction material is the most important factor playing in the thermodynamics. That is this is the main source of heat generations. Of course, it is expected that the friction force will dissipate the energy in the form of heat. So, therefore, it is in the friction material which is to be considered and which gets affected most by the heat generations. Now, the procedure for thermodynamic consideration, thermodynamic analysis is something like this. We see that the temperature rise, we know that the temperature rise, if delta T is the temperature rise, this is related to the total heat lost, and remember the total heat lost will be equal to the total energy dissipated, and we have calculated that total energy is equal to change in kinetic energy of the translating part plus change in potential energy and plus change in kinetic energy for the rotation part. So, that we discussed in the last class. So, this is the total energy which is to be dissipated. So, therefore, this is delta E divided by mass of this body which gets heated times C. C is the specific heat. Unit joule per kg per degree centigrade. So, this is the unit of the specific heat. Now, this is the temperature rise. Now, the temperature gets high, temperature becomes larger if delta E is positive, and that normally occurs during the breaking operations. We have a large input heat input. So, therefore, the temperature will rise. As soon as the temperature rises, then it tries to cool off. We have to use now the law for cooling. The law is the Newton's law of cooling, which says that T at any time, the temperature at any time T, this is T infinity is the environmental temperature, environment temperature minus T1 minus T infinity, this is equal to exponential of minus U times A divided by m C times T, where U is the heat transfer coefficient, A is the area of this of the body where the heat transfer takes place, T is the time, m is usual the mass, and C is the specific heat. Now, T1 is the maximum temperature, T1 is the initial temperature, that is the maximum temperature, because so this is the initial temperature. So, we see that given an initial difference between the temperature in the body and the environment. So, the difference of temperature at any time t is related by these expressions. If we plot a graph, then what we can see is that now if we plot this graph, let us say we plot t infinity and this is t equal time, and we start from one initial temperature T. So, this is T1 and we have measured T over here and it drops exponentially. Now, we see that once we give a heat input, that is once a breaking operation is done, then the temperature goes high to a limit T1 and it drops down slowly depending upon the various factors like U, A, M and Cp, and also the difference, that is the difference between the body initial temperature of the body and the environmental temperature. Now, suppose after time T1, let us say after time T1 we apply another breaking. So, again after time T1 breaking is done, what happens? There is a temperature here and again the temperature goes up. So, now we have another increase in temperature and it comes down slowly. Maybe after 2 T1 we apply another breaking operations. So, again the temperature raises. So, if you look at the final temperature distribution, it looks somewhat like this. The final temperature distribution is something like this one. Now, it may reach such a periodic cycle, that is repetitive cycle after some time. So, it is possible to have a steady state. Now, once the steady state is reached, then of course, we can have further analysis, then we can use another familiar law of heat conductions or heat transfer. Again this law is due to Newton. We have then this law. Now, this is valid only for such steady state conditions. In the steady state, of course, the heat transfer equation looks somewhat like this: Q dot rate of heat transfer is U times A times T minus T infinity, and this is nothing but delta Q divided by dt and U A T minus T infinity. So, dq is equal to U A times T minus T infinity dt. Now, we integrate from, let us say, 0 to T 1, and again this is the integrations. Now, this is the total heat input, and this will be equal to delta E, and that is equal to U A. Now, T temperature varies with time, and we can use this following law, that is T 1 minus T infinity times e to the power minus beta T dt. This where beta is again U A divided by m c. Now, if you use that, then what we get is when we integrate here, then after the integrations we can find the following results, that is, this is the final result we get: T 1 is equal to T infinity plus delta T. Delta T, if you remember, delta T is nothing but delta E divided by mc. So, delta T divided by 1 minus e to the power minus beta T 1. So, this is the final expressions for maximum temperature rise. So, T 1 is the maximum temperature, as we have already noticed that T 1 is the initial temperature, which is the maximum temperature. So, depending upon the breaking cycle, that is T 1, and the parameters like beta is equal to U times A divided by m c, and delta T is the temperature rise, which again depends on delta E and m and c, and T infinity we have the value of T 1. Then usually this T 1 is limited by design considerations, for a simple reason that the friction material gets deteriorated if the temperature is increased beyond a certain level. So, in that case T 1 must be less than T max, which is given from the design, and this depends on U A, m c, etc. Now, heat transfer coefficient, it could be written U has two factors, one is radiation factor. Now, the heat may be radiated or it may be convective. So, this is the coefficient of radiative heat transfer, and this is convection. Then the convection heat transfer may be altered if we blow air or use some ventilation, etc. So, we have another factor which is the ventilation effect. So, F b is due to the, so this is the ventilation factor. So, therefore, we will have to choose H r, H c, F b such that this T 1 gets limited to some value. So, this is roughly the thermodynamic considerations. Of course, it is not that easy, and this is a very rough estimate and only could be used for that part which is taken to be most effective for the heat generations, that is which part gets deteriorated more. Normally this is the friction material, but there may be other situations also. Now, this is roughly the thermodynamic considerations. Now, we have the friction. Now, how to decide the friction material? Then the friction material, we see that the friction material will have the following characteristics, that is high and reproducible coefficient of friction. This is very essential, because the friction coefficient has to be high and it must be reproducible, that is it should not deteriorate from one time to time. Then imperviousness to environmental calculations conditions, that is maybe the moisture, it should not be impregnated with moistures, because moistures may deteriorate the effect friction material, characteristics of friction material. Ability to withstand high temperature, that is very well understood. High resistance to wear, again very much needed, and congenial to environment, because the friction material gets worn out. So, it gives it dissipates dust in the environment and various other things. So, it must be congenial to the environment and it should have some flexibility, because the disc may or the drum may vibrate, or there may be various vibrations in the machinery. So, it has to be accommodated, and this can be accommodated by the friction material. So, this must be little flexible. Now, these are roughly the friction materials. Now, normally the friction materials available can be classified. So, if you want to procure the friction material, then we will have to look up into the chart supply given by the suppliers, but the common friction materials are woven cotton lining, where there are cotton linings which is impregnated with resins and then it is polymerized. These are used for the heavy machineries. Again, woven asbestos lining, here the flexibility is little less, but is same is almost similar as cotton lining. Instead of cotton we have asbestos. Then molten asbestos lining, here we can have some metal also. This may be used for the drum brake, normal drum brakes. Then molded asbestos pads or sintered metal pads, here we have the sintered metal, the metal normally copper or iron they are used, and this has to be sintered. We can have some cermet, that is where instead of metal we can have some ceramic components also. This is very much used nowadays. So, these are different friction materials. Now, we come to this conclusions of this lecture, of these two lectures. We have studied different kinds of brakes. Now, the most important thing of the brake is the friction material. The friction material has to be chosen such that it is able to withstand high temperature, it is not susceptible to wear and tear so frequently, but these friction materials, the characteristics of friction materials are again found in the design handbook. Normally there are few things which are specified, the maximum pressure which could be withstood or the maximum temperature of the friction material. The coefficients of frictions are given for the dry conditions, for lubricated conditions, as well as for the greasy conditions. So, there are different conditions, we will have to look up into the table. So, this is roughly a brief overview of of different kinds of brakes and brakes as far as the designing is considered. We have also considered the thermodynamic aspects, which is very important, and a designer must consider all the aspects when he wants to design such important items in a good machinery. Okay. This is all for today. Thank you very much.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the NR Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theatres, and from the quiet fibre-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility